Hello. Today I tell you something about my PhD thesis. There I was concerned with capillary problems for a special kind of liquids. I divided my talk into three parts. At first I give you a short introduction, then I say something about comparison principles, and at last I show you my asymptotic results. What have I done? Roughly speaking, I computed the ascent of liquids in some kind of cylinders. Therewith, I can compute the liquid in the cylinders, and as one can model some kind of pores in porous materials by cylinders, so one can compute the absorbed liquid in these porous materials. And if one knows the amount of liquid in porous materials, one can find some properties of these materials. For example, the distribution of the pores and the kind and the size of the pores, or for example also stability of these materials, or permeability of sieves, and of course also the absorbing capacity of liquids. So it has a lot of applications in physical chemistry. Okay. As Ray told you, this is a very famous equation. He said at first Da Vinci had a look on the ascent of liquids in cylinders, but I'm sure that Da Vinci didn't know this equation. I think Taylor or something that was one of the first, and Gauss, who found this equation. And here we have some boundary condition. That is, but as Ray told you, that there are some boundary angle established in cylinders. And to find something, to find a solution of this problem, this theorem of Conquest, Finn, and others is a very important tool. That is, if V is a solution of our problem, and if we have some other function we call comparison function, which is W minus, and if this W minus satisfies property 1 and property 2, that is not equality in ours, that is not equality, but inequality. Or as Ray told you, this term is called TU. Yes. If this comparison function satisfies inequality here, so we have for the solution of our problem also this inequality. That is, we can find an upper solution or a bound for the solution. And if we switch the signs here, then we also can switch the relation here, so we can find upper bound. I gave you a weak version. That means I assumed that the boundary of omega is in C1. In fact, it's sufficient if we assume a decomposition of omega, that is, if omega is composition of a null set, smooth set, which is in C1, and the third set, sigma alpha, and on sigma alpha we assume condition 3 that W minus is less or equal to V. So this is a more general condition. But in my thesis I was concerned with a lot of boundaries which are smooth, so I give you this version. For example, I was concerned with circular cross sections or with the ascent on a vertical wall. Of course, a wall is a very large cylinder, an infinite cylinder. And of course, the ascent of liquids between two parallel walls can also be modeled as a cylinder. And I needed the more strict, the theorem with the decomposition just in the case of the corner. You see here is some point where the boundary isn't smooth. And when I was interested in the ascent of the liquid near the boundary, I had this domain, and so I used here a boundary where I had to know something about, where I had to know that the solution is bounded above and okay. What is the strategy to find the solution? It is one have to look for a suitable comparison function W, and this W should have a simple structure. What does that mean with simple structure? I have to prove condition 1 and condition 2 for this comparison function, and if it's a very complicated structure, then it's very hard to prove these conditions. In general, the comparison functions have this shape, a function f plus minus a function g. Then the comparison function yields this inequality, f minus g is less or equal to the solution, which is less or equal to f plus g. That is, it's equivalent to that the absolute value of f minus 3 is less or equal to g. You see, this makes just sense if the absolute value of g is less or equal to the absolute value of f, otherwise we couldn't get new information. So I was concerned, Ray told you the example of liquid like water or oil, and I was concerned with some liquids where with very small dielectric constant. Water has a very high dielectric constant, and if we have small dielectric constant, like if we have liquid helium or liquid rare gases, then an additional potential appears, namely the so-called disjoining pressure potential. It's defined by some integral, and after evaluating the integral, which is a really hard job, we have P is some constant times d to the power of 3 minus p, where p is greater than 3. That is, we have the second condition that the big capital P tends to minus infinity as x tends to omega. Oh, and here d is the distance to the boundary of omega. And this disjoining pressure potential leads to this new boundary value problem, where we have two differences. At first, here is the additional potential, and we have to replace the boundary condition by some limiting process. Okay. Okay. And this perturbation causes a new behavior. That is, here we see again the classical case where always some boundary angle established, and this potential is reasonable for the ascent on the boundary. That is, there establishes no contact angle, but a very thin liquid layer. And maybe you know that if we have a beaker filled with liquid helium, then the helium climbs the walls and tries to leave the beaker. And the disjoining pressure potential is the reason therefore. So we have to find something new to prove this, to find some solutions. But we are lucky since we can prove a similar comparison principle as before. And this principle, together with this disjoining pressure potential, yields some asymptotic results. You see, it's nearly the same theorem as before, but this guy has to be deleted. It's wrong. W has just to be in C2, and the first condition is replaced by this condition where this term also appears. And the proof is nearly the same as Conkers and Finn did before. Here, responsible is that this term, this guy, P is monotone increasing in W. Okay, then we have the same theorem. Let's come to some common setting. That is, we assume the divergence of TP is bounded. Then I claim that P is independent of W, and we assume that P is independent of W. Then this comparison function satisfies condition 1 and condition 2. That is, we have to prove that this guy becomes positive. So we insert the definition of W, then we can, by definition of TV, Tp this constant, and that is, we are led to this equation, this plus p and minus p delete each other, so we are led to this. By definition of Tp, no, by assumption that this guy is bounded, this guy is also bounded. And so we can choose this constant a, that this term becomes positive. That is, if Tp is bounded, W of comparison function W satisfies condition 1. And since p tends to minus infinity as x tends to omega, Tp tends to 1. That is, the comparison function satisfies also condition 2. So we have this result that our solution is always asymptotic equal to this guy as x tends to the boundary of omega. And yes. Okay, some examples for I had a look on the on this setting, the classical capillary tube. I was also concerned with the ascent on liquid on a wall and between two walls, and I could prove that in these three cases the divergence of Tp is bounded. So in these three cases, always the solution depends on, has the same asymptotic behavior, that is d to the power of 3 minus p pi. And where d is the distance to the boundary. And in the case of a corner, there the divergence of Tp was unbounded. So I had to add some additional term in my comparison function and found out that I also got the same asymptotic behavior. But I couldn't compute the divergence, this term p, in the case of the corner for arbitrary small p. I had to restrict myself onto p equal to 6, since the integral I had to evaluate was very hard and I couldn't solve it for arbitrary p. But p equal to 6 is the physical most relevant case. Okay, let's summarize. If we have this boundary value problem, we have the same asymptotic result for 4 different cases. And the solution always depends on the disjoining pressure potential. That is a very amazing effect, since, for example, if we are concerned with the corner, there the ascent of the liquid depends strongly on the opening angle of the corner. And here the opening angle plays no role. Okay, this leads to some problems. The first problem is to generalize the results for arbitrary cross-sections and for arbitrary p in the case of the corner. And yes, after the results, I'm interested in computing some asymptotic expansions. And of course, another important fact is the existence of solutions. There are some papers which are interesting for the classical case, but I don't know if one can modify these techniques to find a solution, an existence proof for my case. And last but not least, most pores can't be modeled by cylinders, so I have to look what is with other cavities, for example, spherical ones, or slit cavities, which are also cavities like the parallel plates, but parallel to the x-axis. That is, we have formed these cavities, and there are my observations doesn't work. Okay, so I thank you for your attention.
Questions from the speaker?
So why is there, is the general theorem says all 4 cases you have the same asymptotics, or it just happens?
Yes, my main result is that I always have this behavior in the boundary. Of course, in these 3 cases, and in the 4th case, for the special case, p equal to minus 2, 3. Yes. And I think that it'll be for arbitrary cross sections, but I have to prove. Right? Oh.
Can you give maybe some physical idea of what your lowercase p is? I mean, you said p equals 6 is more physically relevant. Is that something that's easy to
Oh, it's in the case of water, water is some polar molecule. It's a dipole molecule, and so the electric forces have the most important role in this case. And there are other forces called van der Waals forces, which have and therefore from this disjoining pressure potential arises. And these are forces, they are between every molecules, charged and uncharged, and polar and unpolar molecules. But they play a small role when there are some electric charged molecules.
Other questions?